So today I am going to talk about the work that we have going on, or that we're exploring and thinking about on the computer systems push inside of the expedition. In particular, one motivating trend here for computer systems, and I'm not going to belabor this point too much, is that which is going on with Moore's law. The fact that Moore's law is coming to an end. And what I mean by that is this era of exponential improvements in single thread performance, in a single processor with a single core that we can execute on our single threaded application. That's been coming to an end. It's been coming in for for some time, and although we've been seeing still significant increases in the number of transistors that are available in underlying processors, the way that's been exposed to us is through more cores, more parallelism. And so I'm not going to get into too much around details about things about parallel computing models, but instead think about what Moore's law is telling us about how perhaps we're going to get better single thread performance coming to the future. And in particular, if you look at the computer architecture community, there are a couple of directions that they've been pursuing and thinking about that I'll characterize as either heterogeneous or statistical computing. In the heterogeneous setting, researchers have been considering ways of building domain or application-specific hardware accelerators that allow you to just map specific applications or parts of your application down to an accelerator. On the other side, statistical, and what they're doing here is actually exploiting new computing substrates that just fundamentally return different styles of results. And so just to concretize that a bit more, heterogeneous computing, if I take my TensorFlow or PyTorch program, I have this, this eternal question: do I run this on the CPU, GPU, the TPU? What is the particular deployment context that I'm working in? How do I make this decision? And the heterogeneous computing model, sort of in its full fruition, takes this perspective of trying to figure out how to decompose perhaps very small parts of your application to run on a wide variety of general purpose hardware components, such as a CPU, down to a very highly tuned application-specific component, such as a TPU, which has been specifically designed for these machine learning workloads. Right? Now, on the statistical computing side, the way I characterize this is, quite simply with a couple cartoons. Where on the top, we have our traditional computing, where I take an input, I pass it into my program and execute it, quite normally, and I get a single input on the outside, assuming I'm working in deterministic context. But in these new statistical computing models, we're thinking about, or what we're seeing are models like quantum or analog or stochastic or approximate computing, where what happens is you get an input, and as an output, what you get is a distribution over outputs. And so there are these fundamental questions about, well, what's the probability that I get the correct result if I execute my computation on this type of alternative substrate? So that gives us to what I'd say are some of the emerging trends that are going on in computer systems and how we think these will evolve, where what we need to be able to do now is fairly precisely characterize, say, the performance of a given application on a given piece of hardware, but also now even its behavior. What does it actually produce on some given hardware that's been given to me? And so what I'd say is, the challenge that we're seeing now is that on the left, what we'd like to do is go from a program, a hardware specification, and then both a performance model and behavior model, and then be able to learn how to map this to, well, this sea of potential hardware components that we're going to see down at the bottom. And so this is one of the major challenges that I'd say that we're seeing coming up in the computer systems area in the future, which is, how do you effectively navigate mapping software in an automated, scalable way to just the sea of different systems that may be showing up, so that we can still continue to execute the applications that we so care about. So in this talk, what I'm going to do is I'm going to talk about our work on learning neurosymbolic performance models, so just the performance model of this work, of this diagram. And in particular, I'm going to talk about some work that we have coming up in micro quite soon, called DiffTune. With the goal is that we want to use synthesis-like techniques to synthesize parameters for programmatic performance models. And what we're going to do here is we're going to use a differentiable surrogate optimization technique. And so together at the end, what we get is a interpretable program where we've learned its parameters via deep learning. And of course, I'm not going to get into this into any much detail, but beneath all of this, of all these systems that we're building, there are very interesting questions about what do these neurosymbolic programs mean, right? These are now real valued probabilistic differentiable programs, and the programming languages community and aspects of the systems community haven't really fully explored, I'd say, a lot of the semantic concerns. And so that is one place that we do, as a group, actually spends quite some time thinking about what are the semantic challenges of these systems. So anyway, so on to performance modeling. So what is the performance modeling challenge? So the one I want to talk to you about is this, where I want to talk about, predicting the time it takes for a basic block to execute on some piece of hardware. And this is critical. This is critical to the grand emerging challenge that I talked about, but it's critical to a wide variety of different performance sensitive tasks, where the idea, at least in the way that I want to explain it, is I want to take some assembly code, linear sequence of assembly code instructions, and then predict how many cycles it actually takes for this thing to execute. Specifically in this steady state, if I had an infinite number of these things looped end to end. And so we're going to call that throughput. Now, so the reason why this is a hard problem is because one, your modern processor is actually quite complicated. This is a cartoon diagram of Intel Skylake architecture, and it's quite detailed in that instructions come in through this front end that we see at the top left, transfer through many of these various pipelines, being translated down to a lower level micro-op representation, they're being scheduled, executed on specific execution units, and then, of course, retired, and as well as dealt with various memory concerns. And so this is, if in principle you want to build a highly precise performance model, you are thinking of modeling many of the aspects of this cartoon, and each of these have their own individual logic and parameters associated with them. And what makes this even more so difficult is that this is the real picture that we actually have of this architecture, where we have some hints, but really the best access that we have is via measurements, where we can run code on the underlying processor to get results. Right. Now to these hints, I'll talk a bit about these hints, and it's hard. Intel does provide us some hints, right? So it provides us a wide variety of textually written documentation, so thousands and thousands of pages in the Intel manual. I've got instruction specifications, optimizations that the processors do implement, parameters, instruction throughput. So a lot of it's there, and you see a lot of tables. But these are all, as Intel will admit, approximations, where they actually say, if you go and look through this material, all tables in this appendix are estimates. Actual performance can vary from somewhat faster to significantly faster than what's reported, right? And the reason why is because this is just a very complicated machine. And it's very hard to precisely pin down the value of some single parameter that they can give you as a useful abstraction, or a precise abstraction in all cases, right? And in fact, if you were to sit down, or you're a performance engineer, if you're working in the LLVM compiler infrastructure, what you're going to do is you're just going to abstract away a lot of these details and build a performance model that has a few simpler components that you'll go ahead and model with parameters. And then, so what you get is a very simplified setting where you pass in a basic block into your abstract model, and then you get a number. All right. Now, to explain this in more detail, just to see how really challenging this is, I'd like to go through an example here. The example is, how many cycles does it take to compute 100 iterations of this following instruction? Now, of course, I do not at all expect you to know what this instruction means, but we can go and dig through the Intel manual and figure out what this means, right? You can find the appropriate page, and it tells us this is actually a bitwise XOR of some vector registers. And so we can rewrite that to be something that's more interpretable, which says I've got some register R1, and I'm going to set its value to be R1 XOR R1. Now, what I can do is also go flip through other parts of the Intel manual and now get some of the base parameters that Intel offers to us. Where it's going to say, for this particular instruction, here's the latency. So it takes 1 cycle to compute this instruction. And then here's the throughput. And the way to model this number is, what it says is, if I have 3 instances, independent instances of this instruction, I can complete all 3 in a single cycle. And so that's the way to think about it. All right. Now, so what is this, to the top line question? In principle, you'd hope this was enough information to recover it. And when I go through this talk and I give it in person, one of the first things that comes up is this should take 100 cycles. And this is, if you look in LLVM's implementations, it does actually say 100 cycles. And the reason why is because it says, well, this instruction instance assigns to R1, but it also depends on R1. So there's this dependence. And of course, I can't finish computing one instruction until I've finished computing one of its prior dependencies, right? So you get 100. There's 100 instances of this instruction, and each take 1 cycle. Makes sense. Now, if you spend some time, or if you're up to speed on your bit twiddling hacks, you know that R1 XOR XOR, or any value XORed with itself, is actually going to give you 0. And so actually instead you can rewrite this code to look a little bit more like this, where it just says R1 is equal to 0. And sure enough, if you go clawing through Intel's manuals, you'll find that it actually implements this optimization. So you have to find a whole nother part of the manual to go hunt this down. But you'll see our instruction in there, and it says, yes, these actually have no execution latency. And therefore, we can actually change this so that all 3 of these execute in the same cycle, as we'd expect. So 3 based on our throughput number. Now, of course, you would hope. I mean, this is making more sense. We're getting closer to the real number. But if you measure this, what you actually see is you get the number 25. And the reason why is because once you've made this change, now you're actually getting bottlenecked by an entirely other part of the processor, which has a different specification where it can actually process 4 of these in the same cycle, right? So starting from our very reasonable understanding from the get-go, we can see that the actual measured performance goes through many, many different perturbations and optimizations before you actually get to the result that we care about. And so what it means is that in practice is if you are building these types of models, what happens is this: you have your abstract model at the top, you have your actual processor at the bottom, you take some set of programs that you'd like to characterize and actually use to characterize or test your model. You passed one through the top, you pass them through the top, pass them through the bottom, you take the difference to see where your model is inaccurate, and then you refine, right? Now, if you look at this, you can see what we've got is sort of your standard just training loop in a machine learning algorithm, except you've got a human here in the loop, right? So some work that we did a while ago is what we did is we went and we took this observation and said, why don't we just replace this with a neural network and try to use gradient descent and see if we can actually just learn performance models raw out of x86 basic blocks. And the answer was actually, it's a astounding success. Yes, we can do this. And essentially, with our models, we can halve the error of both LLVMs and Intel's own proprietary tools that we don't have source code access to. So we can cut those error rates in half. And the way that we did this is, there's some minor details to the network that we use, but I'm not going to delve into that too much. But what we really did is, a lot of the work went into the data set measurement and collection process here, finding 1.4 million basic blocks and measuring these according to a fairly thorough assessment of the basic invariants that we want to be true of timed measurements for this system. And so, like I said, I'm not going to get into too much of the details here, but the major distinction here that we've seen is that with our IFML model, there's no featureization. So this is all done with basically just learning representations, representation-based learning, where we're taking raw x86 text and actually able to produce these predictions. And so this is a nice point of distinction versus much of the previous work that's ever been in this space where people do this hand featureization. So the result is, if we go back and look at our example, we get the following, right? LLVM was 100, Intel's IACA came in at 25, and IFML, our learned model, comes in quite close, right down here at 26.8, all right? So that was nice. So we went from this, an abstract model that you have to write by hand, to a much more precise neural model. But it would be nice, and certainly given the charter of this expedition, but to explore, what is a neurosymbolic model, right? And in particular, with IFML, if we wanted to give a prediction, let's say to a performance engineer to say, this is how long your code takes, go off and fix it, they don't really have a working explanation on what to change, right? And so instead, what we've been exploring are these neurosymbolic models. And in particular, what we did is, if we go back to the slide that we had before, we took a look back over to IFML and said, well, could we actually go ahead or to not IFML, but to LLVM, we said, could we find ways to learn LLVM's parameters, right? It's this large, discrete simulator that actually gives you a trace and explanation for why it gave a prediction. Could we actually figure out a way of actually learning those parameters? And so the answer is yes. And so this is some work that we have just coming out in Micro next week, where what we did is as follows. So LLVM MCA, this is the simulation tool that we were talking about in these previous slides that's inside LLVM's source base. So LLVM, this is a very highly used compiler infrastructure, if I haven't said it already, that's used in many, many devices. And so this LLVM MCA model is used to validate many aspects of some of the back-end optimizations that are in LLVM's implementation. And so this program that we're looking at, it's got 10,000 lines of code and actually 11,000 integer parameters, integer value parameters that we'd like to learn. And, I'm not going to explain this in detail, but it has a fairly precise simulation, or more precise than, the cartoon that even the little, abstract cartoon I showed before, where through each one of these stages, there's a whole set of parameters. So instructions come in, they're dispatched, they sit in a reorder buffer until their dependencies are satisfied. They then get scheduled on execution units. And those execution units, everything in this pipeline has a whole set of parameters associated with it. Fully 11,000 in total when we actually look at the instructions that we have. Now, to learn this, if we think about using some sort of heuristic search, this space is just too large, and we validated it versus some baselines, some random search baselines, and even banded-based search baselines. And instead, we decided to go a different approach, where what we did is use differentiable surrogate optimization. So the idea of surrogate optimization is it's an old technique where what I do is I have a model that I'd like to optimize, and I'm going to replace it with a surrogate that is easier to optimize. And so here, what we do is, this is a characterization of the optimization problem we would like to solve, where F, think of this as our simulator, this 10,000 line of code simulator that we have. And what we want to do is find a minimal set of parameters, theta, that essentially minimize its loss, given a data set D and some loss function that we have available to us. And what we do is we translate this optimization problem where the only difference that we're going to have is instead of optimizing our simulator, we're going to optimize F hat, which is this surrogate. And what we're going to do is we're going to choose this surrogate to be a neural network that approximates the behavior of the simulator, conditioned on a set of parameters. And so what this means is we can now apply gradient-based optimization to this differentiable neural network, and then take those parameters that we learn and then put them back into our original non-differentiable, highly parameterized simulator. Now for the learning problem itself, so this is the surrogate learning problem. And just to break this apart, we're trying to find F prime or F hat, what is the best half that we find? Well, it's one that minimizes the discrepancy between this function that we're learning, and our original simulator. And based on our previous results, what we were fortunately able then to do is actually use a variant of ithmol to then learn a surrogate for the simulator itself. Ithmol did a good job actually learning core physical measurements and the physical behavior, and we've actually been able to configure it also to learn this simulated behavior as well. Now, just pictorially, what does this mean? So if you were to plot these, let's say the sensitivity of LOVMCA's prediction is a function of changing one of these parameters. This is dispatch width, is the parameter we're changing. What you can see is it has this different response, and that's that blue dashed line. And what our trained surrogate does, what it does is ends up interpreting this line. So via this interpolation, we can get precise behavioral characterization, but again, this is now going to be smooth, and so it's something that we can actually optimize. Now for the results, so at the end of the day here, it works quite well. From scratch, we're actually able to learn 11,000 parameters that are better than the expert tune parameters. And this is all vastly better than OpenTuner, which is again a fairly sophisticated search-based technique. And so here, this was a success for us. And if we go back to our running example, DiffTune, what it does is it gets this result, the parameters that we learn. We actually predict 27 for this example versus ithmol's 26.8. And as well, we get a nice interpretable trace through this entire simulator for someone who wants to consume that trace and understand why this prediction is as it is. Right? So to wrap up there, this work that we've been doing here is just a core part of this larger challenge. So learning performance models, but there's just a broader challenge here of thinking about learning behavioral models and also learning how you actually translate these programs themselves down to the wide variety of different hardware systems that we may see in practice. And so I didn't talk about it here, but we do have some work as well as thinking about the compilation problem and how we can turn the classic compilation problems that we have into learning problems where we can apply a wide variety of reinforcement learning-based techniques. All right. Now for future directions, I'm not going to delve in these into too much detail, but there are a lot of shared future directions with other work that's been going on and other thrusts inside of that expedition. So thinking about data generation, how do I actually manipulate our process to uncover underexplored regions of the data space? Or how do I do constrained optimization? As we're doing this surrogate optimization, what we'd like to be able to do is actually account for parameter programmer specified constraints and invariants that need to be true among parameters for them to be valid. And so these are active directions that we're pursuing. I think they'll also have great synergy with some of the other thrusts that we have going on. Right. And so to wrap up, talk mostly about the systems work here. There's a whole set of also semantic work that we think about, because again, these are very different computations that we're thinking about, where things like differentiable languages are really new in some sense, and that we haven't fully explored all what it means for a program to be differentiable, given that the various types of differentiability that are actually available to us. And so to wrap up, this landscape of hardware systems is changing. Heterogeneity and statistical computing seem to be coming, and there's something that we have to do. So we hope some of the techniques that we're going to explore in this expedition will help us tackle these emerging challenges that are coming up. So that's it. Happy to take any questions.